Thank you very much, Michael, for the introduction. So I'm very grateful to the organizers, of course, for having invited me to this second act, or should I say, second round of Kobayashi's Fest. And the aim of this meeting, as it is announced by the organizers on the webpage, is to highlight and celebrate Professor Kobayashi's deep and pioneering work in many areas of mathematics. And indeed, I think it will be inappropriate to reduce Toshi's research to some single field of mathematics. He's not just an algebraist or just an analyst or just a geometer. He's a mathematician, and his work is a kind of rainbow, as we saw in his morning talk, combining different colors and different subjects of mathematics in some unit. And exactly, I think that, so my personal feeling that Kobayashi's work has been always driven by this sense of unity of mathematics, and has been always characterized by its elegance and really wonderful ability to make complicated things accessible, simple, natural, and at ultimate stage obvious, in a positive sense of this term. Okay, so maybe should I say happy birthday, but maybe after. So this is the opening. So. And today I would like to talk about one of Toshi's very fruitful idea, which gave rise to the so-called F method, which is a powerful tool to analyze branching problems for different types of representations through explicit constructions of symmetry breaking operators in concrete models of infinite dimensional representations. I think several talks during this week will give a more detailed account of this theory. So I will concentrate my presentation today on this notion of symmetry breaking operators and discuss some particular properties of these operators. And I would like to understand why it happens that sometimes such operators are differential operators. Okay. But maybe before, just I would like to make clear this notion. If we have a following problem, so it was already mentioned this morning, if we have a branching rule for a given representation of a given group, so what do we understand by this? So we consider a representation of a given group and fix a particular subgroup. And then want to understand what happens when we restrict our representation to a particular type of symmetries, to some subgroup. And it turns out that in a quite large setting of representations, group, subgroup, we may produce a meaningful decomposition. Meaningful in this sense that it may be probably a direct integral of some Hilbert spaces, but it will be parameterized by an appropriate set of unitary representations of the subgroup, and then some representations of the subgroup will appear, maybe many times, and then we have to sum up such representations. Of course, all the difficulty of this construction is to understand the measure on the set of unitary representations of the subgroup, understand the multiplicity function, which in general is not is defined almost everywhere, but not explicitly always. And of course, stated as it is, this problem is very difficult and even unprecise, but maybe in my today talk, I will concentrate on the case where so G and G prime are real reductive Lie groups. Okay? And pi is a unitary representation of G. So in this case, in this setting, at least we are sure that such a decomposition do exist, such a measure is unique, and we can define almost everywhere the multiplicity function. And it was already mentioned in Toshi's work that, of course, we have to, the analysis of this function is very complicated issue, and construction of the measure itself is really the core problem of the branching rule. And if we know such a formula, if we know the explicit decomposition, then we may wonder what kind of operators can we get going from initial space, the space of on which the restriction of our initial representation acts, to some given irreducible component. And an element of such a space of continuous G prime homomorphisms from the left-hand side to a given irreducible component will be referred to as a symmetry breaking operators. Okay. And of course, we may wonder, so maybe question 0. So when such a symmetry breaking operator does exist, and basically this is the question about the branching rule itself. And if we suppose that we know the answer, but sometimes maybe it's not necessary to suppose, but for simplicity, let us consider that we know when such a non-trivial symmetry breaking operator exists. Of course, 0, of course, always symmetry breaking. But another question that we may ask is when and why such symmetry breaking operators turn out to be differential operators. Of course, the answer depends on the framework, and as I said, in my today's talk, we choose the realm of real reductive figures for many reasons. Not only the fact that we know, we may say many things about the branching itself, but also because in this case, interesting representations are essentially infinite dimensional and can be realized explicitly in some geometric models. Namely, we can see them as sections of some appropriate homogeneous vector bundles. And we will use very deeply this rich geometric structure and exhibit explicit constructions of such operators. Okay, so we choose the realm of real reductive Lie groups because of the geometry. I may even ask another question 2, saying why question 1 is interesting or relevant. Why should we talk about differential operators? So I don't want to make any, how to say, epistemological speculations, but differential operators attracted a lot of interest since they appeared since 400 years, basically because of the role they play in the modeling physical reality, of course, but also because they are in some sense kind of exceptional objects, singular objects. And in my today talk, I would like really stress on this fact that they have some singular properties. So they are singular in some appropriate sense. Okay, now maybe I will continue here with my first paragraph, and I would like to make clear what does it mean differential operator. So we would like to extend the usual notion of differential operator in the setting which will be appropriate for our problem. And so let V x be a vector bundle over some smooth manifold. Say X. We may, of course, consider the space of smooth sections of this bundle. And we endow it with natural Fréchet topology of convergence of sections and their derivatives of all finite orders on compact sets. So we need topological structure because at some point we have to talk about continuous operators, not only just arbitrary operators. And also similarly, we define another couple. So say W, Y, be another vector bundle over another manifold Y. And we suppose that we are given a map, a smooth map, between base manifolds, Y and X. Smooth map. Okay. Okay, then I think now I'm ready to state to give a definition of what we understand by a differential operator between spaces of sections on associated to these two vector bundles. So definition 1. So a continuous linear map, say T, from C infinity of X V to C infinity of Y. W is a differential operator if it respects the supports of sections. So if you consider the support of T of F, the image of F by our operator, then transported by our map on X, then it should be contained in the support of the initial function. Okay. So this property we choose as being the definition. And usually I will use notation. We will write diff for this vector space of such maps. Okay. All right. So maybe a couple of remarks. So this definition means that our operator is local. So what does it mean, local? In the sense that for any open set U in X, T defines its restriction, say TU, such that TU goes from sections supported at U to those supported on the pre-image of U. Okay. First remark, and the second remark is that our definition is consistent with the usual one, namely if x is y and our map P is just the identity map, then this definition 1 is equivalent to the usual one by a theorem due to Petre in maybe late 50s or beginning of 60s, saying that differential operators in the usual sense do respect the support of functions of sections. Okay. So this is the first point. Now, so we have continuous linear map between nice topological vector spaces, and in this setting we have the Schwarz kernel theorem, which asserts that we may associate to such an operator some distributional kernel, which will express explicitly this, the effect of this operator. So by Lorentz Schwarz kernel theorem says that there exists distribution, or distributional section of tensor product vector bundle, but I will make it clear. T prime, a distribution on the product of xy, which is a section of the tensor product vector bundle of the dualizing vector bundle of V, tensor with W, such that. So maybe I make it here, please. Okay, so we use the dualizing vector bundle here because we rather see distributions as generalized functions. This is the reason. Such that, first, the projection on the second variable is a proper map, at least on the support of this distribution. And we may obtain the effect of our operator on sections by applying this distributional section. Then we may define a following set. Delta of capital Y, it's kind of diagonal, which is composed by pairs of points, image of Y, Y. So it's an element in X times Y. So Y is arbitrary in our second manifold. Okay. So it's a subset in X times Y. And then, maybe I formulated here, we have the following characterization. A map T from C infinity X V to C infinity of Y W is a differential operator in the sense of our definition, if and only if the support of the corresponding Schwarz kernel is contained in the diagonal set. maybe, so the proof itself is not complicated. Use the structure theory of distributions and the definition of the support. So it can be, this property can be translated on the level of the Schwarzschild. So maybe I wanted to give some examples, but maybe the time is running.
Can I just check the differential operator is the same as the differential operator between the original bundle and the pullback of this one?
Yes. So maybe I skip some examples because the time is running. But indeed, we recover usual situation. Maybe just one example. So if P is a submersion of two manifolds, so E, Y to X. Okay. So we may choose coordinates on X and Y in an appropriate way. So let's say X, Y, Z, J be an atlas on Y, such that Xi's form an atlas on X. Then such a differential operator is necessarily of the form that we should expect. It's a sum over different multi-indices of length dimension of X, H alpha X Z, D alpha over dx alpha, where H alpha X Z are matrix valued sections, smooth sections valued sections on Y. So we recover what we would like to have. But let me continue. So now we have extra information. Let our manifolds are endowed with some group action. This is the point we would like to discuss. So if both X and Y say admit or say are equivariant with respect to some Lie group, say G, then of course G acts on sections by translations, and in a very natural way we may define equivariant differential operators between these spaces as just, as I say, differential operators which are equivariant. Okay. Okay.
Something there. When you say X and Y are equivariant, you mean V and W are equivariant. You want an action on the fiber as well.
Yes, so first I suppose X and Y are equivariant, and then we construct the equivalent vector.
And then you still want G, not G prime on the right.
Of course. There's no G prime in this story. Yeah, I'm sorry. Okay. Of course, so for instance, if X and Y, maybe a short example, X and Y are Euclidean vector spaces. P is injection, say, and G contains all translations of Y. Then this space is a vector subspace is contained in a vector space of differential operators with constant coefficients. Okay, and moreover, maybe this is an important point. So if we have again more structure, we may go even further. So if it turns out that if x and y are complex manifolds, the map and the vector bundles V and W are holomorphic. Then we may talk about holomorphic differential operators. Then we say that the map T, again, between these spaces is holomorphic, is holomorphic differential operator if it respects the support of global holomorphic global sections. In this sense, U is contained in U of okay, and for notations we will write in a similar way for the space of such operators. Okay. All right. Now, one, there's no two, right? So then two. And again, so I will progressively add some structure and then collect the results from this. And would like to give some, kind of establish a kind of first bridge between this geometric construction, this geometric world, and algebraic ingredients. And I would like to introduce the duality theory. For differential operators. Okay. So now, from now, I suppose that really G is real reductive. So its Lie algebra is denoted as German Gay of R. So U of G is the universal enveloping algebra of its complexification. Let me write it here. And I will use the same type of notations for all different subgroups. Okay? So capital for the letter for the group, German small for with R for the Lie algebra, and without R for the complexification. So I don't precise anymore. So now let's consider just a closed subgroup. Of G and V finite dimensional representation of H. Okay. Then, of course, we may. This data give us a homogeneous vector bundle. So I will call it in the same way, Vx or just sometimes just V, which is associated to this representation. So the fibers are copies of the representation space, and so it's a homogeneous vector bundle over homogeneous space G mod H. And just for simplicity, for concrete formulas, we may identify the space of smooth sections with space of H equivariant functions, V-valued H equivariant functions on the group, right? So this is by definition.
So that's not entirely G mod H, right?
Here.
Yeah.
Thank you. So functions, and on the right hand side, they are functions on G, which are valued in V. And if we act by H through our representation on f of GH, then we recover f of G for any G in G and H in H. Okay. All right, so now I have to erase something. Good. So the last ingredient for the theorem is the notion of induced module. But here's nothing surprising, just I recall the definition. So for a H module for the corresponding Lie algebra V, we define the corresponding induced module for the enveloping algebra. So int from H to G of V as being V with respect to the action of the enveloping algebra of UH. And the induced U of G module. Okay. So it's very standard and natural definition. And of course, if we take H being the Borel subalgebra and V, I don't know, one-dimensional representation, then we recover just a standard Verma construction. So now we may formulate the theorem. So the first theorem today, I would like to state two theorems. So it's due to our work with Toshi. In 2016. All right, so space so let H prime and H be closed subgroups. Of G with, so I maybe repeat Lie algebras H prime and H respectively. Where I consider representations, corresponding representations, V and W be finite dimensional representations of H and H prime respectively. Finally, let G prime be subgroup of G containing H prime. And as before, we use the same notation. We define this homogeneous vector bundles attached to this data. No. Okay. Okay, but here W is attached to G prime. Okay, then there exists a natural isomorphism between the space of continuous G prime intertwiners between this following, no, it's not G prime, it's H prime. No, G action here. W check So the space of continuous H prime intertwiners between the dual space of the initial representation, so contragraduate representation of W, and the restriction to H prime of the induced model on one side, and the differential operators equivariant with respect to G prime between Vx and W. So I call this map dx to y. So this is our isomorphism. Or equivalently, we may formulate this on the level of underlying gay H modules, or gay prime, more precisely, H prime modules.
Oh, I'm sorry, Misha, I have a question here. Here.
Yeah.
So for the duality theorem, you have a W check and the induce from H to G and V check.
Thank you very much.
Thank you.
Okay. Yes, yes, sure, sure. We have to take dual contragraduate representation on both sides, of course. So we consider the corresponding induced modules. And end up in the same space. So I just copy. Okay. So on the right-hand side, we have this geometric object that we introduced in the first part of the talk. And here we connect it with a purely algebraic object, which is a space of intertwiners between induced U-gay modules. Maybe I give you the explicit shape of such of this construction. So it gives the underlying idea. So if we have such a homomorphism, say phi is a map, continuous H equivariant map from W check into induced module. And F is a function on our group that we identify with a smooth section. Okay? then what is the effect of this differential operator? So dx to y of phi, as the theorem says, it's some equivariant differential operator between these two spaces of section. So I apply it to f, and f is w-valued function. So it's difficult to, I don't want to write it in coordinates, so I just dualize with some element of w. Say check.
Well, you just said it's beta. No, here it's correct. So f is here. Oh, so the application is.
Yeah, I apply the operator and then end up in w. And here, so it's a sum of following operators. So we use the right differentiation of our enveloping algebra acting on f and dualize with Vj, where this homomorphism phi applied to w, so phi is, yeah, w check. So phi is a homomorphism. So when we apply it to an element of w check, we end up in the induced model, which can be written as, just by definition, as some sum of some uj's and vj's check. Okay. So very natural and explicit formula, which explains the idea of this identification of homomorphisms with differential operators.
Sorry, Misha. Sorry, so I have a question.
Yes.
So it's f is in C infinity of g or g dash, I mean g prime. I'm a bit
Here?
confused. Yes.
No. G.
Okay.
Initial version was correct. Yes. Time is running. So what is important also is that this theorem, so there are many maybe things to say about this theorem, but what I want to really stress is that it actually holds in the holomorphic setting as well. So maybe I may formulate it in holomorphic setting. And then go to the final goal, but maybe just a few words about the proof. There are several steps, and then of course we have to identify properly the effect of these differential operators, and at some stage use this characteristic lemma that connects our general definition of differential operators with Schwarz kernel and this property of support. But let me reformulate this theorem. It's important in a holomorphic setting. So theorem holds in a holomorphic setting as well. Okay, so let, as previously, GC, G prime C, H, C, H prime C, etc. be complex reductive groups. Okay. So maybe notation is a little bit misleading. They are not necessarily complexifications of our previous groups. We'll see what happens when they are. But in general, let us just consider such a construction. VW be finite dimensional holomorphic representations. Finite dimensional holomorphic representations of HC and H prime C respectively. Then we may construct holomorphic equivariant vector bundles. Again, V will be GC, and W is the same way. Okay, so G prime C, etc. And also we assume HC that HC prime is connected. Okay. We didn't in the previous setting, and this is why I gave two statements in one in terms of H prime equivariant maps and others in terms of underlying H modules. But here we assume that H prime is connected, and actually we don't lose any generality because for applications we will talk about complex parabolic, and the property will be fulfilled. Then we may reformulate this duality theorem in the following way. So there exists a, I don't know, canonical natural isomorphism. Again, I use the same symbols that connect gay prime equivariant maps between induced modules and this time holomorphic differential operators, equivariant with respect to G prime C. So I didn't use this notation, but it's logical, right? So XC is GC mod HC, and so this is a C. And if G prime, H prime are real forms of those groups, of these groups, right? Then, of course, these representation spaces are H modules, also just by restriction, right? And we may wonder when such holomorphic operators, so when corresponding differential operators admit a holomorphic extension. And at least we may give immediately one sufficient condition. So if H prime is contained in the connected complexification HC prime, then there exists a bijection. Of course, always we have an injection, but there exists a bijection between holomorphic differential operators. Can you see here? G prime. And the objects that we defined in the previous part. So here it's GC, G prime. So we may extend our equivariant differential operators to holomorphic differential operators on corresponding complex objects. Okay. Now I think I may erase this, and maybe even the definition of differential operators I don't know, maybe I keep it. And use this blackboard. Okay, now localness and extension theorem. So again, I need some structure. So I try to write quickly. So I suppose again G is connected reductive. Theta is the corresponding Cartan. So not corresponding, but a Cartan involution. And so we have maximal compact subgroup. We have G mod K, which is a Riemannian symmetric space. And we do assume that it is also emission. Okay. Then there's a crucial geometric assumption that will connect the geometry of G mod K with the geometry of G prime mod K prime. Okay, so as I have not so much time, so I do it a little bit quickly. So there exists a characteristic element in the center of K, such that the Lie algebra breaks into three pieces corresponding to -1 eigenvalue, 0 eigenvalue, and +1 eigenvalues of the adjoint of Z. We know that there exists a complex structure on G mod K due to Borel open embedding, and we suppose that, so we would like to have same reach geometry on G prime mod K prime, but we wanted to have in a compatible way with the larger one. Okay, so we may have two emission symmetric spaces, and we would like to have them compatible. So let G prime be connected, reductive subgroup of G, say also theta stable, so it doesn't cost anything. I think we don't lose any generalizers saying that. And we said K prime is the intersection of K and G prime. Then we assume that this characteristic element Z do belong to the Lie algebra of K prime. Okay, so this is a crucial assumption, and if it happens, then G prime mod K prime is on the Hermitian subsymmetric space, or symmetric subspace, or subsymmetric space of G mod K, and the embedding G prime mod K prime in G mod K is holomorphic. Okay. Okay. So one may think of several examples. We may consider the case when G prime is the diagonal of G, for instance, then it works, or we may choose a G prime to be an appropriate symmetric subgroup playing with the corresponding involution. But maybe I continue without examples. And so I suppose that G prime is a symmetric pair. Okay, so G prime is okay. V is a finite dimensional complex representation of K that we extend trivially to a holomorphic representation of PC. So PC is the just the subgroup of GC, which whose Lie algebra is K plus N plus. Okay. So just acting the N plus trivially, we can extend it, form again holomorphic equivariant vector bundle here over PC this time. And then, so XC is the complex flag variety here. And maybe I write it, it's important. So the restriction to the open set G mod K in XC defines a J equivariant map, or maybe just to directly message J equivariant holomorphic vector bundle. I call it V for and we have a natural action of G on global holomorphic sections of this holomorphic homogeneous vector bundle. Okay, this is important. It comes from the geometry of the complex flag variety which lives above. So this is an important point. And of course, the holomorphic differential operators, G prime equivariant, that arise in this setting are contained in this much larger space, total space of intertwiners of G, K, V. Right. But surprisingly, the theorem that I will state asserts that it's not just inclusion, there's a bijection. So we can identify these two sets. And so I formulated this theorem. Again, it's a joint work with Toshi. And there are two parts. So the first one really concerns the local operators in this sense. So this is why we call this result a localness theorem, which says that any G prime equivariant map, G prime homomorphism, from OG mod K V to OG prime mod K prime. W, with the previous notations, is given by a holomorphic differential operator in the sense of this definition 1. So this one, I wanted to keep it on the blackboard. With respect, so of course you remember that this definition depends on the choice of the map. With respect to the this holomorphic embedding to the between G prime mod K prime and G mod K.
To finish soon.
Yeah, 2 minutes, is it okay?
No.
Okay, thank you. Okay, so in other words, the space is exactly what we wanted in the first line. And we may say even more. So our, I don't know, dream, if I may say it this way, mentioned already somewhere. Yeah, here, about the extension comes true, and we may formulate the extension result as well. And actually, so the second part, and then I finish. So extension. Any such differential operator extends to a G prime C equivariant holomorphic differential operator with respect to the embedding of complex Flag varieties. So YC GC prime or PC prime into XC, which is GC mod PC. And this natural injection that I mentioned, something like it disappeared. Too many blackboards. So this natural injection is actually a bijection. Maybe I stop here, and then I may...
Okay, thanks very much. Let's thank Michael for a lovely talk.